We want to use the classical method of hypothesis testing, that's 6 steps plus verifying requirements, to perform the following hypothesis test. So according to a survey in 2013, and we'll take this as a national survey, the rate of acquired infections from patients among registered nurses was 87 per 10,000. So particular hospitals implemented some new safety procedures for nurses and staff. During 2014, they recorded 6 infections among 1,450 randomly selected registered nurses. Is there sufficient evidence at the alpha 0.05 level to conclude that the new procedures are working? So if they're working, then that should lower the rate of infection. So that would be what we mean by working. And the word rate in this context, the rate of acquired infections, we said 87 per 10,000. That's really a ratio. So this is a proportion value. That's a p-value. So this is going to be a proportion hypothesis test. So let's decide what some of the information is here. Our 87 per 10,000, that's our population proportion. That's population information. Okay, so our hypothesized proportion, P0, is going to be the 87 divided by 10,000, which is 0.0087. And then we had 6 infections per 1,450 randomly selected registered nurses. So this is going to be our sample size. That's N, 1,450. It's our random sample. And then X is going to be 6, our number of quote-unquote successes. So an infection is a success here. And remember, X over N is going to be our sample proportion. And then alpha is 0.05 is given. So first let's verify the requirements, make sure we can do the hypothesis test. So the sample is a simple random sample. These are randomly selected registered nurses, so we're good here. We need to verify N, P0, 1 minus P0 is greater than or equal to 10. So N is 1,450 times our P0 is 0.0087 times 1 minus 0.0087, and that is equal to approximately 12.5 if you compute that on the calculator, which is greater than or equal to 10. And then we need our sample values to be independent of each other. That's going to happen if the sample size is less than 5% of the population. So we need that 1,450 to be less than 5% of the population. So is 1,450 going to be less than or equal to 0.05 times our population size? Well, if we divided both sides by 0.05, that's just saying that our population would have to be greater than or equal to 1,450 divided by 0.05, which is 29,000, and there are certainly at least 29,000 registered nurses in the U.S. So this one's okay. So we verify all the conditions. So now let's determine our null and alternative hypotheses. So remember, you look at the alternative hypothesis. That's what you're trying to show. We're trying to show that these procedures are working. So we would want to show that in the alternative hypothesis that the proportion is lower than what it was in the population. So this is our hypothesized proportion, the 0.0087. And so if we list our H0 and our H1 alternatives, so if it works, then our population P is going to be less than 0.0087. The proportion of infection is going to go down, lower rate. If there's not sufficient evidence to conclude that, then we're just going to conclude the null hypothesis, which is that the proportion equals 0.0087. So remember, null is always stated as an equal. select our level of significance. That was given to us as alpha equals 0.05. And now we're going to sketch our rejection region on the distribution curve and then determine the cutoffs on the rejection region. So this is a p less than test. So that's a lower tail test. So that means our rejection region is going to be on the left-hand side. So we're going to have a cutoff, let's say right here, and then alpha equals 0.05 is going to be the area to the left of this z-value, this critical z-value right here. And that z-value, we can get that from the table of common z-values, which is in the formula sheet for the chapter. And that is here. So this is hypothesis test for proportion, classical approach, which is what we're doing. And we are looking at a lower tail test, so p less than p0. And if we come down here, our rejection regions for common values of alpha, so alpha is 0.05 here, and then this is a lower tail test, so z less than negative 1.645 is what we want there. So this is negative 1.645. So now we want to compute our test statistic, and if that test statistic is less than negative 1.645, then we reject the null hypothesis. So this is our rejection region here to the left. So we would reject H0 if our test statistic falls in here. That's our rejection region. Okay, so now we need to compute that test statistic. So the formula for the test statistic here is p hat minus p0 divided by the standard deviation of the p hat distribution, the sampling distribution for the sample proportion, and that's p0, 1 minus p0 over n square root. And remember, we use p0 here instead of p hat because that's our known proportion, that's our population. So remember, p hat here is x over n. That's our sample proportion. And for us, x was 6. There were 6 infections in the nurses out of n equals 1,450. Which is approximately equal to 0.0041. And I'll keep 4 decimal places there because our population proportion had 4 decimal places. So let's go ahead and do our plugins here. So our p hat is 0.0041. We are subtracting off the population or hypothesized proportion, which was the 0.0087. So this 0041, 0.4% instead of 0.87%, looks like it's significantly smaller. We'll see if it's statistically significant when we calculate our test statistic here. So then we divide by the square root of p0 is 0.0087 times 1 minus 0.0087. And then we are dividing that by our 1450, which was our sample size. And if you compute this on the calculator to 2 decimal places, you will get negative 1.89. So negative 1.645 is here, negative 1.89 is going to be to the left, about maybe right there. So this is our test statistic. So that's our z-test, and it is negative 1.89. Okay, I'll just use an arrow there. And so our test statistic does fall in the rejection region. So if the test statistic falls within the rejection region, we rejected the null hypothesis. Okay, so we are going to reject H0, reject our null hypothesis. Lastly, we want to state our conclusion. So if we reject the null hypothesis, then we are going to conclude the alternative hypothesis, which is H1, that our proportion is strictly less than 0.0087. Okay, so in the sample information here is sufficient to reject the null hypothesis, would be another way to say that. Now, we can double check some of our work here using StatCrunch. So if we open StatCrunch, remember we want to go to Stat, and then we are doing a proportion test here. So it's proportion, one sample, and then we have summary data. This is not raw data that we're using. Our number of successes were 6. Our sample size here, the total number of observations, was the 1450. And then we were testing against P0 was 0.0087. And then it was a lower tail test, so the alternative hypothesis was P less than 0.0087. And we click Compute. And then notice here that our test statistic here, our z-stat, is negative 1.87. And here we got negative 1.89. We're getting just a little bit of round off error because these are 4 decimal places, and then this is a very small number. So a little bit of round off in doing this by hand. The exact value is negative 1.87, and then our p-value here is 0.0307. So if we did this from p-values, notice that our p-value equals 0.0307, which is less than 0.05, which was our alpha. And remember, if your p-value is less than alpha, then this is telling you that you reject the null hypothesis. You reject H0, which is what was indicated up here because our test statistic fell in the rejection region. So again, when you do it from p-values using StatCrunch and you see that p is less than alpha, geometrically what that means is that your test statistic falls in the rejection region. So you're rejecting the null hypothesis. Because it's meaning that this is the area that's to the left of negative 1.89, and the 0.05 is to the left of negative 1.645. So since there's less area here, that statistic has to be farther out to the left on the distribution. That pushes it into the rejection region. So this is just a double check here to compare the classical method to the p-value method.